Sound check. Sound check. All right, things work as they usually do. Hello everyone. Welcome to the Vulkan stream. So it is likely that this week, as I tweeted, will be the last two scheduled Vulkan streams for this year, because next week is Thanksgiving and then it's December, and then I have plans for almost every weekend in December, and then there's Christmas, and then I won't even be in the country probably, so things get a bit crazy. In December we might still do like an ad hoc stream, but the truth is a lot of the stuff that I wanted to do we kind of did. There is one big thing that we did not get to, which I'm hoping to do this weekend, which is going to be occlusion culling. And then there's a couple of obvious extensions to the renderer that we could do at some point later, like we don't support textures yet, but there's nothing inherently complex about integrating textures into the renderer that we have so far. So we might still do that, but it's just not that interesting. So the occlusion culling seems like the biggest complex thing that we haven't done yet. So we will be doing that. I have a few documents open because we'll need to do some math to sort of have the occlusion culling work out. And there's also, I think I mentioned this paper on stream before, but the core of the idea that we will be using was discussed in this talk, GPU-driven rendering pipelines. We'll be using a slightly different, like a slight modification of this that I will go into right now. Also, at some point the stream will probably be interrupted because I have a delivery coming, because the air in California is amazing the last week or two. So I got like an air freshener or some air purifier, which may help a bit. Although it's way better today than it was. The air today is unhealthy. The air yesterday was very unhealthy. So we are making progress. So without further ado, let us start, and I may talk about future stream plans more tomorrow, but today I want to focus on trying to get occlusion culling going. I don't know if you'll make it today. It's a kind of large topic. There is a lot of things that could go wrong, but that's fine. If we don't make it today, then we'll finish it tomorrow. And then I have one other small thing that I might want to do if we have time for this tomorrow. Anyway, so occlusion culling. So just a brief recap, right? So what do we have so far? We are able to draw a lot of meshes. We are doing frustum culling. We are doing LOD selection, right? Let me let me quickly change the parameters of this scene to make it more obvious as to why what we want to do today may be important. So I wanted to, where is this? Yes, I want to change the field of view back to 70, and I want to make the meshes larger. Let me see how that looks. Yeah, let me, for now, oh great, yeah, for now let's just render kittens exclusively. Okay, so if you look at this level right now, right, so we are rendering, we are taking 10 milliseconds to render apparently 135 million triangles. There is some LOD selection that we are doing here. There is some frustum culling that we are doing here. But so here's like a large kitten, right? And clearly behind this large kitten, there is a lot of small kittens that we are still rendering. If we had wireframe mode, it would have been obvious, but I mean, we kind of know we're rendering them. Same for this one, same for this one, and then there is all of these moderately sized kittens that still occlude a lot of the kittens behind them, but we are still throwing all of these triangles at the GPU and hope that the GPU copes. And the GPU does, it's a powerful GPU, right? But if we had occlusion culling, then we could spend less time actually rasterizing things that we don't see. Now, there's a lot of different ways to do occlusion culling, and they have different trade-offs. But what I kind of want to explore is, hey, what if you did not have special occlusion geometry? Like the only thing that we have is this mesh that we compute level of detail for, but there's not a special occluder that we have for these kittens. And I want to just automatically do occlusion culling on the like raw geometry output of this without without having special assets, but also without having any frame delays for occlusion to kick in. Like in Unreal 3 and Unreal Engine 3, they use this occlusion technique. They might still do this in 4, where you sort of do occlusion queries, and then next frame or 2 frames later you read the results and you act on them, and then you turn around the corner, and then for a frame or 2 you just don't see something that should have been there, right? So I want a system that's perfect, that's perfectly conservative, and that doesn't require custom occluders. And that's what we will try to build today and tomorrow. There's a couple of different ways to go about this. We will do one of them. There might be other tweaks to this idea, potentially using some other NVIDIA extensions that are available on this card, but we won't be doing that today. We will be doing like sort of general purpose, no extension, something that could work almost anywhere, occlusion culling. So here's the basic idea. Let me switch to this, and I will be mostly writing for the next few minutes. So so there is an object that occludes another object, right? And we can know the occlusion sort of status because we have a depth buffer. So imagine that we have already rendered the depth buffer for the scene, right? Obviously this requires actually rendering all the objects, but we'll solve this problem later. So then what you can do is, there's the buffer and there's like a kitten, and what you want to do is this. There is an object that you're rendering, and you want to do sort of an aggregate depth test where, say, you're rendering this object that I'm drawing as a sort of red rectangle, right? And you want to ask, will any pixels of this object possibly be visible, given the fact that we already have a depth buffer? Now, we have a million objects that we are trying to do this test for. Excuse me. So the tests must be fast, right? Like ideally the test for this object would be constant time. So one way to do this test is to just take the center of this object and do a depth test. Just sample the depth at this point and ask, hey, is the depth at that point in the depth buffer closer to the camera, which in our case it means like larger because we have a reverse Z, but it doesn't really matter. Is it closer to the camera, right? And if it is, then your object is behind. For the test to be conservative, like here, right, the center of the object is actually outside of the occluder, so it would work out. But if it was inside, then the test could say, yeah, I'm totally behind an object, but parts of your object are still visible. So to have a conservative test, what we will do is we'll build a pyramid, which you can think of as just a MIP chain, which it kind of will be, of depth, right? So we'll take our depth buffer, we'll downsample it many times, up until we get to like 1 by 1 or something, right? And each reduction will be 2x. So in each reduction, we'll take a 2 by 2 quad of pixels and downsample it to 1 pixel. But we won't average the depth. We will use, so for us, as a brief refresher, so we are using infinite, not infinite, but more importantly, reverse z. So for us, z near is at z equals 1, and far, which we don't really have, is at z equals 0. So when we are building this MIP chain, we will use conservatively the minimum depth, minimum like reduction operator, so that we'll take the 4 depth values in the quad and then take the minimum of them and write them to the pixel in the MIP chain. And then we'll do this recursively, and then we'll have a pyramid. As a result of this, in each pixel, we'll have the minimum of depths in all of the pixels, kind of like contained in the pyramid, if you look at this as a hierarchical grid, right? Which means that we can look at the pixel and say, well, if the minimum depth, which is the farthest depth, right, is still closer to the camera than the object that we are trying to draw, then the object must be behind all of them, right? Because this was the farthest depth, which means we don't need to draw it. And the reason why the pyramid is important is because if the object is large, we can pick the level of this pyramid where in that level the object is smaller than 2 by 2 pixels. So we'll take this object, right, the red quad, and then we'll say, hey, so in the high level of the pyramid, this object is like, 100 pixels. But if we go down like 5 levels, then the object looks something like this. So in the magnified view, there's like a quad, right? And then there is this object that is kind of small, right? And it's completely contained within a 2 by 2 pixel radius. And then what we will do is we'll sample these 4 pixels and then take a minimum of them, and then compare this value against the some closest point on this object to the camera, and then reject the object accordingly, right? So that's the general strategy, and since for each object we have a bounding sphere, we will be able to use bounding spheres to do these tests. Now, the caveat is, I said we'll start with the depth buffer, we'll build a project depth pyramid, and then we'll reject objects against this pyramid. The problem is, to build the depth buffer, you have to render all the objects. So that's kind of a catch-22. So the way we'll solve this problem is we'll say, well, it is likely that if the object was visible in the last frame, it will still be visible in this frame. So what we will do is we'll do a 2-phase render. So phase 1 will be, oh, this is not the right scale. I have to resize things both on my tablet and on my monitor for them to be visible. So we will render objects that were visible last frame. And if the camera barely moves and if the objects barely move, then this is almost the entire scene. We will still do frustum culling on these objects because it's really cheap for us to do, and this means that if you suddenly turn the camera 180 degrees, then you will still get frustum culling on all of these objects, right? So this is kind of what we can, this matches really closely to what we are already doing. So we'll run almost the same code that we do right now. So then we will build the depth pyramid for occlusion, right? So then the problem is there are objects that were not visible last frame that might be visible now, right? Because the camera moved. Then we will do the phase 2, which is render objects that were invisible last frame. And So this, but we will do occlusion testing, right? So we will not render objects that are actually invisible in this frame if they are occlusion tested. And we will also do occlusion tests on objects from phase one, right? And we'll record the visibility status of all of these objects, including occlusion tests, for the next frame. So what I'm expecting to happen is this: we will render the first frame. We have no information about visibility from the previous frame because there was no previous frame. It's the first frame, right? So we'll render all objects with frustum culling, etc., exactly the same as we are doing right now. Then we'll build the depth pyramid, and then we will do, for all of the objects that we have rendered and the objects that we haven't, we will like redo the visibility tests with occlusion tests this time, and then we wouldn't render any more objects because we've rendered everything that could have possibly been visible already, right? But we will record the visibility status with occlusion for the next frame. And then on the next frame we can start this cycle of, we know what objects were visible last frame, we'll assume they are still visible and not occluded, we'll render them, we'll build the depth pyramid, and then we'll render false positives. So we'll render objects that weren't visible last frame but are still visible now. And we will confirm this sort of false negatives where if the object was rendered this frame, it doesn't mean it was actually visible, which should improve our culling efficiency for the next frame. And then the hope is if the camera doesn't move too much, and right now for us the camera doesn't really move at all, then the results are perfect. So that's kind of the plan. We will try to get there, and we'll see how it goes. And some things that we will be doing today might be kind of inefficient, and this is okay. We will, today the goal is to try to get it working. I don't know if we can, but we'll try. And if we can, then maybe there will be some things that are slow, and then tomorrow we can clean them up. So we are not going to be using occlusion queries for this, right? Because the problem with occlusion queries is you have to render some object for them to kind of work, and this is not very efficient. We want to render millions of objects, so we want to be able to test millions of objects very, very quickly, which is what this technique will allow us to do. Occlusion queries do not allow to do the same thing very quickly, right? They can scale to like thousands of objects, fine, but if you're dealing with millions of objects, it's not a very good idea necessarily. So before we actually do all that, I wanted to do a brief cleanup on the culling shader. We wrote some code last stream where I said I don't know if the compiler like optimizes this well or something, and turns out it doesn't. So we'll quickly fix that just to get a better baseline for our work today, but also to sort of get back in the hey, we are writing code flow. So right now we are rendering a million objects. Culling takes 0.14 milliseconds. I think this is with vsync on. I won't bother toggling vsync back off. The shader that we have right now, it has a path for this fast ballot operations that I talked about last stream. We can enable ballot, but turns out that most GPU compilers and NVIDIA seems like it's doing that. Like, we weren't seeing differences performance-wise between ballot and like naive atomic operations. And it looks like it's just a case that the compiler just optimizes these atomic operations to write the exact same ballot code that we were writing ourselves. So this is just making things a bit more complicated for no real gain, so we'll remove them. Because we'll need a second shader like this that also does occlusion culling, and I don't want to be dealing with that. Oh, also, nah, that's fine. This probably can stay for now. So let's check that this thing still works, right? So we're still running at 0.14 millisecond. Now, one thing that, let me look at this. Yeah, so the thing that we were doing, and there's a to-do comment here now, is that we were taking the mesh structure that has a small array of like 8 somewhere. It has a small array of 8 elements that describe the level of detail data. We copy it to a variable locally, and then we index into this variable using the index that is computed dynamically. And this is not, generally speaking, a very safe construct, because on the CPU you could interpret this as this is a copy on stack, and this is an indexing operation on the stack, right? There's no real stack in the shaders, so this is not very optimal. Like, compilers can emulate this, but it's not very fast. On CPU, you might be used to saying, hey, yeah, this is a copy. Why am I copying something to stack if I don't really need to? So on CPU, you may be saying, hey, yeah, obviously this should be faster. Shader compilers don't support references, unfortunately, or pointers, so the more sort of direct way to write this code, and let me just for clarity, extract this into local variables. So a more sort of direct way to do this is, say, let's just have the exact same expression again that we used to have and read from that. And if we do that, nothing changes, but it used to. So let me enable vsync, I guess, so that I can get more stable timings, and hope that it actually does change. I mean, disable vsync. Oh, and I maybe should, let me confirm the clocks. Okay, yeah, so we're maxing the clocks out. Oh, you know what? I updated the drivers since. Damn it. In my old drivers, this wasn't optimized. Let's just... okay, whatever. In my old drivers, this was faster, but I guess in the new drivers, it's the same. So maybe the new driver compiler is better. Doesn't matter. Just forget I said anything. And so, yeah, the other thing I wanted to try is... right now we are running 32 thread warps. It should be okay on NVIDIA, but it's definitely not going to be okay on AMD, because on AMD you want to use 64 or more. And I wanted to just spend a couple of minutes sort of making sure that I can change this to 64 and everything will just work. The problem is right now on the C++ side, when we do the compute dispatch, we are saying the single warp transforms 32 draw calls, or like processes 32 draw calls. So let's divide by 32. And if you change the 32 number in the shader, then this code breaks. So I just want to make sure that I can do that without breaking the code. For that, I want to compute, so in the shader sort of declaration, you specify these local size attributes. I want to extract them from the shader in the same way we've been extracting like other information like this. So I want to have I don't know, like let's say even 16Z, it doesn't really matter. Yeah. So I want to extract this from this PRV, or you know what, whatever. Like, there's no point saving memory here. So when we parse the shader, if we look at the shader declaration, then this op execution mode says, hey, we will be declaring some parameters for the shader that specify interesting things about execution, and one of them is local size, and here we see the numbers from the shader 3211. It's a 3-dimensional size. So I just want to quickly parse that out. execution mode. So what should happen is you have one word for the opcode and then 2, 3, 4. Well, what should happen is you have 1, 2, 3, and then based on this variable you might have, based on the value of this value, on the value of this value anyway, based on this value you may have additional data in this instruction. So we should say that this thing is at least 3, and then the data definition or the kind of whatever is here. I don't know what it's called. Is it just called like mode SPV execution mode local size, right? Yeah. So this is the mode, and then if the mode is this, or I guess we can do switch again. And in this case we should have 3 words for the sort of what we are specifying, and then 3 words for the values. So it should be 6, and then let's just read them out. So this should be 3, 4, and 5. Let me switch to debug. And then in theory here we already have this value in our shader data, so we can say that we will specify the number of draw calls rounded up to the local size x, which is the number of draws that each work processes. And then and then we are running with vsync, so as usual we get a validation error. Yeah, so this value is 32. So we parsed it out successfully, 3211. And now we should be able to just change the shader to say 64, and then maybe things will be faster, or maybe they will not be faster. Let me see. So 0.14 right now. And then if I change it to 64, then it's 0.08, so it's substantially faster. Well, does it work? It doesn't work. It's substantially faster, but it doesn't work. Oh, right, yeah, because here we are being sloppy. So this value should be... I mean, really, I think this is local invocation index. Do we even use this guy here? Or this guy? So maybe this should be just that. No. Oh, not local invocation index. Hold on. I need to look at the spec for this. There's some value that... global invocation ID, I think. Yeah, so we are doing this math right now ourselves in the shader, but it's sort of already present in this variable. So I guess we can do this for now. Not ti, like di. 0.14. Let's see if it's any faster with 64. Also 0.14, but this is nicer because now if this code ever ran on an AMD GPU, which it doesn't right now, but it could, then we will be efficient in terms of how we are distributing the workload. So I guess we didn't really make our shader fast. I was like this thing, basically I think with all drivers, the culling, I thought I measured 0.27 something, 26, and then with this it was 0.14, but it appears that the driver is already doing that now, so maybe that was a fluke. Doesn't really matter. Anyway, so now we can start thinking about this occlusion stuff and start actually doing this, right? So there's two things that we need to do that are complex. One is we need to build this depth pyramid. There's like three things. We need to build a depth pyramid, then we need to implement this occlusion test where we look at a sphere, we find the level in the pyramid where the sphere is less than 2 by 2 pixels, and then we sample from this, we take the minimum value, and then we compare it and things like that, right? And then the third thing is, in general, we have to reshuffle our code to run in 2 passes, where we render objects and then do some extra work, and then we render more objects potentially. And then we reuse this buffer with visibility in the next frame. So, yeah, let's start writing this. I don't really know. Should we do the two-phase thing first or not? Something that I want to double check. So let me restore this. This was basically, we'll leave the scale adjustments and the radiance stuff, that's fine, and then we just added local size parsing and cleaned up the shader. Day 13, minor shader cleanup, add local size. This is to make it easier for us to change shader code and for it to still run correctly. Clean up, draw color shader, and use 64 threads in a work group, just in case this code ever runs on empty. You know, it's not actually making our code faster, but it might one day. So we could do the 2-pass thing in theory without building the pyramid, or we can build the pyramid first or something. I don't know. I think we probably should do the 2-pass. We should split things in 2 passes first because this involves some render pass stuff. And then we can build the depth pyramid, and then we kind of will have to in one go, or I guess we can build the depth pyramid first. Yeah, we probably should build the depth pyramid first, and then we'll have to do a lot of stuff after this without really a way to test this. So it could be that at the end of the stream we end with code that doesn't really work, right? And then we'll have to like fix it tomorrow. Something I want to check before we actually start implementing the depth pyramid is I get a feeling that we might need a debugger today, if only to validate, like when we build the depth pyramid, I want to kind of be able to look at it and say, hey, yeah, I think this looks kind of correct. But I don't know if I can do that. So let me quickly check. I know Nsight right now does not work without program, but I think RenderDoc might. So let me first check if RenderDoc works with our code. I have to disable mesh shading because mesh shading is not supported by RenderDoc right now. And I think I have to use the RenderDoc nightly because the non-nightly version definitely didn't work, but let's see. So this is RenderDoc 1.2 like beta as of, you know, yesterday. Let's see if it works, because if it does, it will help us. And if it doesn't, then well, we'll have to sort of ignore debugging as a possibility. I think this is the correct. This is correct. Okay, so that is encouraging. So now let's capture. Okay. So far, so good. So here you can see clearly that our render, we are drawing a lot of objects, we are doing culling. It's getting kind of complex, but we have like, what is it, like 5 real commands that do work. Dispatch, begin render pass, and render pass, draw index, and copy image. We also have some barriers that RenderDoc shows in line somewhere here and some scissor stuff, but it's pretty simple. So yeah, let's see if things actually work with RenderDoc. Oh, what is this? Capture has 4 issues. Shader reference to descriptor set that was not bound. That is a lie. That is not true. RenderDoc might not work well with some of the other stuff that we're doing. Alright, that's a bit of a shame. I was hoping that we would see that we would have a way to debug this code. Yeah. So basically, if I look at this render pass stuff, it doesn't really work. Is that the case? Let me see. No, yeah, view contents. Yeah. Okay, no debugging for today. That's gonna be interesting. That is gonna be interesting. Like, we can build some getter tools to display things on screen. It would be nice to not have to do this because this will take time. Alright, okay. No RenderDoc it is. So to do this depth pyramid building, today we'll use an inefficient version. If we have time tomorrow, we can make it faster, where we will just go one level by one, and then so we are starting with, let's see, so we have this depth target. Should I just do this? No, we'll make a separate like depth pyramid image, and then we'll resize it when we need to. But right now, basically, it's some amount of, let's see, so it's like 1024 by 768 right now, right? So that's like about 10 reduction steps. For each step, we'll just write a compute shader that in a really dumb way just computes the target value, and then writes it out. Compute shaders are just easier to deal with because we don't have to create render passes and stuff, so that would be nicer. When we do this step, we have to take the 4 pixels, and then we have to take the minimum value in them, and then we have to write it out. To do that, we could just do this ourselves, like just do 4 samples. We could do gather 4. Oh, should we do gather 4? I was thinking that we can use a nice sampler extension, but actually maybe we should just use gather, and that will be easier, assuming gather works. And then and then we'll do horizontal min. And then for gather, we might not even need yeah, we might not even need a sampler. Maybe we should use gather. Let's see how that works. So yeah, texture gather, and then we'll still need the sampler variable, and then it will just do the right thing. Is that right? Yeah, okay, let's not use, there's an extension that could be nicer, but let's not use it for now. So let's just start writing this code. So we need the depth pyramid, and whenever we resize the swap chain, we'll have to reallocate this depth pyramid. When we create one, we will start with half the sort of swap chain size, and every dimension we will be reducing by 2x. We are going to be slightly sloppy for now. I'm not sure that the code that we'll be writing right now will be conservative, but I want to get something working first. So I think that's fine for now. So we need this pyramid to have MIP chain. So let us change the code. Where is it? Oh, right, we have this function for resource creation, create image, where we are hard coding the number of MIP levels. So let's just end this. And then we'll need more image views, but we can create them manually. So we need this function really to be accessible outside, and then we'll need a MIP level here as well. So like that. In fact, maybe this image view should be, what are we even using this for? Let's do this. And then instead of so this will be kind of like the view for the entire image, and then we will need to create views for each slice, because we will be reading data from one image view and writing data to another image view, and it's kind of required that they don't alias, because there is no way, unfortunately there is no way in core Vulkan to, I think, to write a pixel into an image's MIP level. So we'll have to do it like that. Okay, so that is fine for now. Now let's fix, so now we need to be specifying that we need one MIP level here, one MIP level here, some unknown number of MIP levels here. Let's do this. Pyramid depth pyramid levels, and let's create vk image view depth pyramid slices, or it's basically MIPs, right? Let's just call them MIPs, or levels, but levels is already so the maximum number that we will really need, like if we had 16, then we could allocate up to, what is it, like 65k by 65k depth buffer, which is probably gonna be enough. So let's destroy all of this stuff. Wiki destroy. Oh, I guess destroy image. And then we need something like this here. And then we'll need to recreate it, obviously. Let's just add a function for this. Here, let's say. Nice. IntelliSense refuses to go to destroy image, but it's happy to go to create image. All right. Yeah, so this should return the number of MIP levels that we need. Depth pyramid. And we'll start with swap chain, with like half the swap chain, because our first reduction step will go from the full depth buffer to the first level of the pyramid. We don't really need the full MIP chain to test against. It's kind of the full like image to test against. It's kind of redundant. In fact, we might want at some point to reduce even the first level here to some smaller value. For now, it's good. All right, so create an image, and then we'll figure that out in a second. And then I want to create views for each individual slice. It's basically this one, where we do depth pyramid levels is that. And not levels, MIPs. Alright, so that should be good. Now, so when we render into depth buffer, we'll need to read this depth buffer from a compute shader to be able to... Oh, that's gonna be fun. No, yeah, that's fine. To be able to write into the depth pyramid. So this kind of needs to say image usage sampled, I suppose. Yeah. And this we won't render into the depth pyramid, but we'll use it as, we'll read from it, but we'll also write to it from the compute shader, and this will need the storage bits. I think this is roughly correct. And we are in debug, and let me reduce the draw count to like 100,000 so that it's faster to load. So that's good for now. Let's see what we didn't do right. Ten is too much. It should have been. No, maybe it's fine. Hold on. The combination of format type, tiling, usage, and flags is reported as unsupported. Oh, we don't really need D32S float. That is redundant. What we need is VK format R32S float, so maybe that's the problem. Alright, so that's better. Oh, and the format here, right, yes. Because we aren't going to be using, we are going to be storing depth in depth pyramid, but it's not like a depth buffer, so we just need a float, really. Okay. Alright, so that is better. We have created the depth pyramid right now, hopefully. So then when we render, this is going to be slightly interesting. We kind of will need two render passes, so let's just do that now, because we need to do this anyway. Will we need two frame buffers? No, I think we need one frame buffer, so that's fine. So we will need two render passes, because the first render pass will clear the depth buffer, render things to the depth buffer, and then store the depth buffer. Then we will compute the depth pyramid, and then we will start another render pass where we can't clear anything anymore, but we also don't need to store the depth buffer. Should I just pass a parameter here? Let's just pass a parameter which is like what should we call it? Yeah, I don't know. So this will be clear color depth, render some objects, store depth for later use. Right, and this will be render more objects, so don't clear anything, and then no need to store depth. So yeah, I mean, it's kind of, you know what, it will be more intellectually honest to just create a second one. Okay, so the difference is previously we didn't really care what happens with our depth data, which is reflected here. Now we very much do care, because we will need this depth data later, so let's store it. And then all of that can stay as is, we will fix stuff up later. And then here we don't need to clear, but we do need to load the existing content, and we do need to store it back for the color. And then for all of this is fine. Yeah, and then for depth it's kind of same thing, we need to load, but we don't care. So yeah, I guess maybe I should have kept it in one function, but you know what, that's fine. So let's just create the second one. And then we will have to destroy the second one. And then, just to see if things work, let's like use the second render pass, but just render nothing to that. And I think we'll have to do scissor setup again. Oh, does scissor and other things like that? Hold on. Render pass scope both, and set viewport presumably both as well. Okay, so this means that you can set these values outside of the render pass and the settings persist. So for cleanliness or clarity or whatever, let's like move these guys out, because we'll have to essentially restart the render pass. So we draw a bunch of stuff, we end the render pass, and then... Oh, there's this triangle counting business that we are doing, so that has to move later. Okay, but whatever. And here we are doing transitions from... Yeah, so we'll need another render pass here, essentially, where we use the other render pass. And I think I don't need to be creating more frame buffers and compiling more shaders and all of that stuff, because there is complex rules in Vulkan about render pass compatibility. Yeah, that basically say that the passes that we have created, they are compatible, so it should be fine. So I don't really need to clear. All right, so let's just do this like this for now. So this is just dummy, we just begin render pass and render pass, there is nothing here, but we just want to make sure that we have set up the passes correctly, and it's all fine. Okay, we don't have validation errors, so maybe it's good. Now, between these two passes, we will need to read data from the depth buffer, and then write data to the depth pyramid. For this to work, we have to do some like memory barrier stuff. So let's do that. So we need to basically transition the depth buffer. Oh, and then we'll need to transition it back. So this is like depth read barriers, let's say, and we only really need one, I think. Yeah. So we were doing depth writes to this value, and now we will be reading this from the shader. And it was depth stencil attachment optimal, and now it's gonna be something else. Now I think I should be able to use, there is this depth, no I can't. Yeah, so this has to be shader read. Okay. This can be inefficient on AMD GPUs because it can like decompress memory, but honestly, it's kind of like broken design in a way. Like I really want to read the depth buffer. So the fact that you want to decompress memory just doesn't work very well with today's renderers. So, and I think this might be fixed in the later GPU architectures. But we won't worry about this at all because we don't even have an AMD GPU to test this on. So we don't care. Alright, so as usual, these things will take a bit of time. I think this is late fragment tests. And then we will be reading this data from compute. So let's just say that, right? I don't know that we need this, but it's fine. And then we just need that. Then here we will be doing some depth pyramid building stuff. So to do build depth pyramid. And then after that, we will wanna use the depth buffer again to render more things into that. So we'll need another barrier that basically flips things back. It would say, hey, we used to read, and now we kind of need to write to the depth buffer. Actually, this probably should be that, because we need, wait, where did the thing go? Okay. Because we need to both read and write from the depth buffer. In fact, I'm not sure if I need read barriers. Do I? No, this part is fine. Probably. I'm not super sure. But here definitely I think I need both. Anyway, and yeah, we want to switch the image layouts back. And then we used to do this from compute shader, and now we need this data in the pipeline stage, early fragment test. And so the reason why I don't know that all of this is correct, but the reason why I'm doing late fragment test here and early here I'm saying wait for the fragment for the depth writes to complete, which I think can happen in late fragment tests. And here I'm saying I guess maybe this should be late as well. I don't know. It probably doesn't matter much. There's a reason why I thought this should be early and this should be late, but maybe this is not true. It's impossible to know if this code is correct. Just deal with that. One day validation layers will start validating this stuff. Yeah, okay, so let's see if that works. Depth only image formats. Oh, I think, yeah, right. When I specify the barrier, I think here there's an aspect mask that I have to specify. Come on. Image aspect depth bit, yes. Let's do this again. Okay, so no validation error, so far so good. Now here I want a loop that says for each level of the pyramid, let's build this level, right? And let's build this level by running a compute shader. So let's write a compute shader that doesn't do anything useful for now. Let's call it depth reduce or something. And the idea is gonna be, we don't really need anything here. We will do a 2D compute shader, say like 32 by 32. I don't know that we need that. I don't think we need like anything here, but we need an image that we are going to be writing things to. And I have never written this code in GLSL, so I don't know what I should write here. But hopefully we can figure it out. Yes, I need an image object. An image 2D object as an output. And I also kind of want a sampler object as an input so that I can use texture gather. So that's what we're gonna do. In location 0, and we haven't used sampler objects at all, so who knows if they work. Do we even need to? Oh no. Oh no. Oh boy. Oh boy. It's gonna be fun. Yeah, we'll have... I just realized that we are missing a small part of the infrastructure that builds pipeline layouts, because we haven't been using images or samplers or anything at all on stream, and we'll have to fill that in. Oh boy. Okay, it's gonna be challenging, but I'm hoping we can get there. Like, when this code actually runs without validation errors, that'll be like an hour later, because there is stuff we need to do. Okay. The idea is simple, right? So we want a sampler. I'm not sure why this is G sampler. I'm not sure what that means. And GVAC. Oh, I guess this is like double versus float. Okay, but the idea is simple. So we'll need a sampler like input, which may or may not be a keyword. I don't know why it's highlighted like this. And we will need an image to the output, which may or may not be a keyword. And then in our program, we'll have the... Let's just do output first. It'll be simpler. And then we'll just say, hey, can I write 0 to this position using image store. Output, and then it's not uint2, it's of course uvac2, and it's not really di, it's like boss, let's say. And then let's just say that we will write 0 for now, right? This is not a very interesting depth pyramid, but it's good enough for now. Yeah, so we'll hit a couple of issues now with that shader, I think. Okay. Yeah, output was reserved word. I mean, out is also reserved word, which is unfortunate. At least I believe it is. Useless application of like, oh yes, it's binding 0, sorry. Wait. Really? Yeah, layout binding 0, isn't it the same thing? It's kind of odd. Maybe it's reacting. Let me, so like, let's call it out I or something like this. Oh yes, uniform. Okay, all right. And now I can actually do layout. Okay, this error was a bit confusing, but yeah, we should do write only image 2D. Okay, cool. So that in theory just clears the image, right? And in theory, you would think that what we can do is say, hey, for each, you know, level of the pyramid, oh, we need to load the compute shader, I guess. right. So then don't need push constants for now. Compute. Yay. I don't know why I didn't capitalize R, but whatever. And then here we just do the same thing that we already did a bunch of times, where we do bind and then like set up descriptors and then do a dispatch. So let's do that. So we don't need to bind, it's like we're using the same shader, right? And then for each level, we for now will just bind the output, which is gonna be depth pyramid mimps I, right? Oops, image view. No, it is an image view. Why is it not happy? Oh, there's no implicit constructor. Did we not add one? Oh yeah, I wasn't sure how that's gonna work out. I think you can basically, let's do this. Still need an image layout, so that's that. Can I just do that? And the pyramid MIPS are gonna be in the general layout all this time, because that's how things work. And then there's no push constants. So then we need to compute the number of waves that we need to use. For that we have to compute the size of the level. So level width is basically swap chain width over 2, which is the starting level, and then shifted by I. And then if level, well, I can just do stud max 1. And then it's the same computation that we've been using, so it's level width plus depth reduce local size -1, depth reduce. This almost begs for a function. In fact, let's add a function. Well, it's not thread count, it's like group count, probably. Single group count, thread count, local size, and then this will be thread that. That's a bit shorter. Oof. Alright, so yeah, get group count, level width, local size X, and then same thing for Y. And this is like a two-dimensional compute shader. And it's not clear if these matter much these days, but okay. So if we run this code, I'm expecting it to not work. Yeah. Yeah. well. Yeah, because we're not really extracting the information from this PRV fully. And there's this to-do comment here, which is replaced with the array of 32 descriptor types, which is exactly why this doesn't work. So I guess we need to do that. Like, there's just no way around this. So that's gonna be painful a bit. So if we look at the culling shader, then right now we are extracting information about the bindings somewhere. Let's do this. Throw call comp.txt and depth reduce. So if you look at the culling shader, then if we search for like binding in descriptor set, we are currently extracting information from this PRV and saying, oh yeah, this must be a storage buffer because we don't use any other resources. Well, guess what? Our compute shader needs an image. And this is the image, but we don't know that it's an image. For us to know that it's an image, we have to follow a complicated process. Damn it. I didn't want to do that, but I have to. Yeah, so I think we are looking at... Oh, uniform constant. Oh, that's interesting. Wait. Hold on. Interesting. So this is not even this branch. Huh. Oh. Maybe things are less crazy. Thing is, I'll need to use samplers as well. Can I not use samplers for now? Let me think about this for a second. It's gonna be a bit junky, but yeah, so ideally what you should do, this is what we are looking at right now when we are analyzing the bindings, and I think this is what has the binding numbers. And what we need to do is to follow this pointer, which is like a type, and then to follow this guy, which is like the actual type, and then it can be type image, or in this case it is type something else. This shader unfortunately is longer, so it's more painful to fish this out. Let me try. I think this is the same thing, and then this is the type, and then this is the struct, right? So if this is the struct, then it's like a structured buffer or like a storage buffer. And then if it's yeah, and then if it's an image, then it's, yeah. Maybe it's better to just do this. So for pointers, we need to gather what they are pointing to. Basically, for each object we need a type, which is either a struct or an image or a pointer to something else. And then here we can analyze this. So I guess we just need to do the right thing. Let's just do the right thing. Okay, yeah. I forgot that I need to do that. When I was thinking about how much time all of this stuff will take, I forgot that I need to do that, which was not smart. But okay. So this is descriptor type. So yeah, descriptor type, like resources 32, and we'll need, let's say, resource types and resource mask. And let's parse this out correctly. Oh boy. Not looking forward, but it's not that hard, but it's just painful. It's interesting that one thing is uniform and one thing is a uniform constant. Kind of didn't expect that. But yeah, so in these IDs, we're currently storing, what is this type? We aren't even using that. Oh, this is the thing that we need to be following. So this is the type ID basically. I should say so. And then for pointers, the type ID will point to this guy, but then we need a kind, and then that, something like that. All right. Okay, maybe this is not terrible. So this points to this type ID. So we need to be parsing pointer. Wait, what? Hold on. Wait. I guess it's type pointer. So pointer has 1, 2, 3 things and the actual sort of declaration. So it probably should be exactly equal. Not sure how exactly these things work out, but I'm assuming it's the same as variable for now. So 2 is the... You know what, let me read the PRV spec because that's gonna be easier. So I need type pointer, right? And I need to know how it's encoded. Let's see. Result, storage class. I'm confused about this indexing. Let me look at variable first. Op variable. Yeah, so here the result is somehow number 2. So this is like first word in the instruction, second, third, and the result type is the first. Yeah, okay. Alright, so point types are different, I guess. Op type pointer. Oh boy. Oh, and I don't, wait, let's do this. So this will be type pointer, and then there is type struct and type image. And presumably there's some type like sampler. So let's just add this here. Okay, so in this the result is the first. Okay, so this makes more sense. So there is the resulting ID and then storage class, which is uniform, but I don't really care about this at all. Well, I can still save it, I suppose. And then it's a pointer, and then it points to the thing number 3. So it's like that. And then let's do the same for type, you know, struct and whatever. Struct, or the sampler and sampled image and image. Perfect. There's 3 things. Sampler and sampled image. Sampled image. Alright, maybe this will not be as bad as I feared. So let's say struct. Struct has at least 2, but then there's also, should be like that, and then the ID, And then we don't care about anything else. It should be just like, we don't care about the struct composition. We'll just use it to figure out if it's a buffer or not. It's slightly sloppy, but I think this will work for everything that we need it to work for. So then if it's an image, it's probably same thing. And then I'm just gonna guess that it's the exact same way for sampler. And then if this works, we're like committing this. This is kind of a lot of work. Sampler, sampled image. I will assume the layout there matches. Pointer, struct, image, sampler, sampled image, pointer. Okay, so I think we are ready to do the right thing now. So if it's uniform or apparently uniform constant, which I did not quite expect. So let's do that. Not sure why exactly the difference is there, but then this is basically a resource. And then what the expectation is that the type ID points to a pointer. So type ID's type ID kind is pointer. And then if we if we look at the kind of the thing that the pointer points to, which is the pointee, I guess, right? Or like the type, really. It's, or not type, but like type kind, let's say. We need to, take this guy and then dereference this thing again, and then this kind, which is actually ID kind. All right. And then we are saying we'd really like it to be one of these, like struct image, sampler, or sampled image, and then based on which one it is, we will figure out what we need to store. Or let's just do switch type kind, and then ID, resource, no, hold on, shader, resource mask, that. All right, so this is what we're already doing right now. This is vk descriptor storage, descriptor type storage buffer. We could in theory also support uniform buffers, but we don't use that right now. And then this is what we were lacking, right? This is why we went through all of this trouble. So we need storage. Oh, how do I know if it's a storage image or a sampled? Oh yeah, sampled image is here, never mind. Sampled image, and then this is sampler. Storage image is stuff that you store or load things into, and then sampled image is actually you use a sampler object to access the resource. And then, you know, unknown resource type. And it would probably be better if we do it like that, so that if the cert fires, we are not recording the use of the resource, and then we can figure that out later. Okay. Whew. All right. Oh, I see. Okay. Oh, okay. This is painful. I think this is the same code that we'll need elsewhere, if I'm not mistaken. Like here, yeah, this is the exact same code, so we'll need to extract this. Gather resource types. Or gather resources, I suppose. Oh boy. Okay, we are close. If this code works, then we are really close. So what I want to do here is I want to make sure that the shaders don't have conflicts, so that if one shader has binding 0, that is an image, then the other shader in the pipeline, which is not applicable to compute but is applicable to other places where we might want to use images, make sure that it's the same type. So if the shader uses that, and then if the mask already has this, then I want to assert that we have filled the resource type. And then otherwise I want to fill it. And yeah, I probably should have kept the name. Hopefully that's correct. And all this trouble is to be able to say this here. And then same exact thing here. Please work. Please work. Okay, I'm done. No. Ah, thank God. Okay, we seemed to have parsed things correctly. I probably should check this. I really don't want to. I hope this code just works. We didn't hit any assertions in parsing any of the shaders that we had, so that's good. Yeah, so... Okay, that's fine. We could just enable this bit. I don't know really what kind of support for this is, but so in GLSL you can annotate images with format, but I don't know, of course, how to do that. So let's figure that out, shall we? So yeah, format qualifier. How does that work? Come on, like, so I want to say this somewhere, but where and how? I wish it would like say. This thing is useless. So I'm gonna make a guess and say that it's like this. No. Really? Thank God. All right. that was a digression. Also, we forgot to destroy something, but whew. I'm really happy this just worked. I will let me okay, so what we have just done is we have parsed a lot more information out of this PRV. All of this was to make sure that when we load our new shader, let me step into that. We don't assume that the fact that we use a resource means it's a storage buffer, but instead we correctly parse this. So I think if we look at our shaders right now, then if there's a shader, there's a resource mask which is 1, and then there is storage image in the first slot, and then everything else is sampled just because things are 0 initialized. So this means that now we can use images, and hopefully samplers and all of that just work as well. And in theory, we are running the compute shader that sort of fills this data with zeros. We don't have a debugger working, so we can't validate that. But the hope is that it works. Let me take a brief pause, because this was hard. So I'll just commit the thing, look at chat, just like take a breath. Maybe do a thing where, you know, yeah, maybe it's stupid to have 2 functions. So let's do that. No, maybe we don't need this guy. Yeah. Where can I read more about this depth pyramid thing, chat? So that's a good question. I think there was a presentation that kind of predates some of this technology a bit, but it talked about a similar thing. Let me see if I can find it. I think it was called rendering with convection or something like that. Haha. Yeah. Which was about splinter cell convection. And I think it talks about something like this as well. Let me see. This talks about why queries are not super awesome. And then this is what we are trying to do, right? We have a depth buffer, and then we want to reduce it to get a pyramid where the pixels use the minimum depth of the other pixels. Here it says max, but we are using an inverse depth buffer, so for us it's min. And then this is the exact same thing that we are trying to do, right? Find the right level of the hierarchical Z buffer, which we are calling depth pyramid. The one that covers the screen bounds with less than or equal to n pixels. For us, n is 4. Yeah. And then it talks about some other stuff. And here it's saying, right, like, so you are trying to do 20,000 queries. Oh, is this the... This is Xbox 360, so... Yeah, this is different. But anyway, so this is saying on Xbox 360, 20,000 queries take 0.4 milliseconds, which is reasonably fast. And it's saying that occlusion queries may be substantially more expensive, especially if the objects are large, right? So in this case, the cost of a query is kind of constant, which is really nice. So yeah, that's exactly the thing that we are trying to do. And I was kind of hoping that we would have a debugger so that we can see this picture, but we don't, so we'll see what we do about that. Do you think that Vim layout allows to be more productive in Visual Studio compared to default mode? I don't know, I don't have a way to compare, right? I cannot use non-Vim anymore, like full stop. My fingers, my mind, everything is trained to Vim. So I don't have a way to compare. I mean, I like it more. And it feels like it makes me more productive, or like it feels like it makes it easier for me to type text. It doesn't necessarily mean more productive or less productive, but I don't, again, have a real way to test, right? Is that true? I'm not sure. Anyway, so... Okay, so we are rendering, we are like doing 2 passes, but the second pass does nothing, and we are building the pyramid, but the pyramid builder just clears things. So we have to fix that and the other issue. So we have to start filling the pyramid with correct data in this compute shader. And oh, I'm surprised, actually, by the way. Oh, there is no push descriptor. So this is, we are not doing the thing that we should be doing, I think. Because like this is just, there should be a layout transition here somewhere. But it's not, it doesn't exist. So... Oh, and also this will have to become more complex because it doesn't allow for just one view transition. Okay. So we'll have to fix that. Yeah, we should have been doing it better for the first use. Or actually doesn't matter if it's the first use. Let's do that. So before we fill the pyramid, yeah, let's just depth read barriers. So what I didn't do is I didn't sort of, like when in the first frame it's not clear what the format of the depth pyramid is, and it seems like it might not matter because we render into that, but per spec it sort of does. We're not getting validation errors, but that's because right now this function isn't validated by the validation layers, and there's a bug on this, and there's a pull request for this on the validation layer GitHub, but it's not merged yet. But what we need to be doing, kind of, is we need to be saying we are gonna write to depth pyramid now, and we don't really care what happened to this before at all. Oh, and this is somewhat not true. This is probably fine. Anyway, so we don't really care what the state was. It's undefined, but the new state should be general. So I think this should be more correct. Okay. And the other thing is, so now that we have this working, let's hook up this sampler. I really wish there was a simple way for me to like visualize this data. Is there a simple way for me to visualize this data? Does Blit image support format reinterpretation? Let me have a look at this. Sizes can differ. Does it do format conversion? Okay, I think we can do this. All right. I think we can actually simply hook up this flow to show us the contents of the pyramid. That would be super nice. Okay. So, that would be nice. Okay. Let us try to do that now. Because I really want to be able to just look at this, right? It's convenient to be able to look at the pyramid. So let's do something like bool pyramid, like visualization, or like visualize pyramid. And then let's say when I press P, oh, let's call it debug pyramid. Okay, let's try to do this. I'm hoping it will work. So we already are right now copying out the color image to the final swap chain. And copy has to match sizes on both sides. It can't scale. And our pyramid MIP levels are like random sizes, right? But I'm hoping that what I can do is that, so if, like, I'll still do this thing here. We're already doing, yeah, okay. So I'm hoping that instead what I can do is I can do vkcmd blit image that will blit from the depth pyramid image to the swap chain, right? No, wait, to the swap chain images, image index, and this guy is general, and this is TST optimal, blit region, and then we'll just use VK filter nearest so that you see the pixels, hopefully, of the pyramid on screen. Alright, yeah, if this works, I think it should, but I'm not sure off the top of my head. But if it does, that would be amazing. So let's see what we need to fill here. Oh, I guess we can start like this, because that's probably the same thing, right? MIP level is really useful because we will be able to, for now let's just say 0 explicitly, but that is what will make it possible for us to switch between different levels of the pyramid. So everything else we just leave as is, and then there's this SRC offsets. Bounds. Is this like minimum and maximum? It's kind of interesting. And it's not this size. But yeah, so I'm assuming this is like corners of the copy of the blit. So we want to just copy the full image to the full image. Oh, but we'll need to compute the, okay, let's do this. Okay. So this is gonna be 0, 0, 0, and this is gonna be. It's really weird that there's no real, like, okay. I will assume the reasonable thing, which is that swap chain width over 2, debug level. And here is just swap chain width, swap chain height, and 1. Let's see if this works. Conversion from, oh, I see. Okay. And I'm assuming the same thing here, yeah. Okay. Let's see if that works, or if there's validation errors. There's validation errors. Invalid usage flag, right. When we are creating the pyramid, we are not saying that it's okay to copy from it. We should. Come on. Okay, so this is an example of the validation warning that should really be in a completely separate layer. So I think things work because we are clearing things to 0 and we see black on screen. We can check this, but there's a warning every frame now that says for optimal performance, the layout should be transfer source optimal. This is like debug code. Why do I care? Yeah. This should be a separate validation layer. It has no place in the default one. Like, there should be, like, if you want some VK, like, performance validation or something, sure. But this is just obnoxious. Let me deal with that. I should file a bug on this, because, like, what if I need it to be general? Should I, like, transfer it? Why should I transfer? Maybe I should just not print warnings, but okay. Save flags wiki. Oh yeah, this is this performance. Oh, okay. You know what? Like, I've never seen any other performance warnings. I'm assuming they're not terribly useful. Let me. I want a warning. I want to see the warning again, so that they can copy this, paste this. Warnings like it doesn't seem like validation layers should be in charge of this. It seems like, you know, vendor profilers should be in charge of this or something. Anyway, so okay, so now we are ready to. We might want to remap the range, but we can't do this during Blitz. But that's okay. So let's try to just do a copy from an image to an image without a sampler first. and then I can commit this code because it's a really like makeshift, not really correct depth pyramid, and then we can do the right thing later. I'm not sure why I switched to Vim, but okay. So image, let's call it an image. So yeah, the not correct thing to do is to do this. Presumably. Okay. So when we create the first pyramid level, we will read from the original depth buffer, and for all subsequent ones, we will read from the one that we just wrote to. And also, we need the barrier after this call, which we will add in a moment. I don't know if we want granular barriers necessarily. It's kind of, yeah. We might just want to slap a barrier here, like this, sort of. All right. And we already have this barrier here, which is slightly weird. And that's fine. So yeah, the first argument will be the sort of source depth, let's call it that. And if it's the first level, then it should be, can I just do this, I wonder? Like, will this work like this? Well, obviously with actual arguments, like, does this work? Or do I have to manually? Yeah. That's what I thought. So for the first MIP level, the sources here for us apparently. For the first MIP level, I will want to read the original texture, which is the depth target image, and it does not have the general layout, it has some other layout. We've transitioned it to shader read-only optimal here. So these layouts have to match, by the way, I didn't really talk about this at all, but these layouts have to match whatever is specified in your pipeline barriers when you bind images to stages. And otherwise it's the same thing, but we will be using the, oh come on, the previous MIP. Oh, it's the view. Oh, wait. Better now? Okay. Right, let's see. Still black. Now the problem is a lot of these values are really close to 0. Or the problem might be that a lot of these values are really close to 0. Well, actually, some of them... Let's increase the drop count. Let's try to get something, like ideally you would have some shader that actually does this remap so that it's easier to see the values, but we are just blitting, so it's not. Let's do this. Okay. Let's do this. Okay. Okay, so if I do that, then this should roughly be the distance from the camera, and then maybe if I divide it by 100 and I get something reasonable. I don't get anything reasonable. Okay, maybe our shaders, maybe our reduction doesn't work, or maybe our visualization doesn't really. Well, this is like this is super incorrect to do here anyhow. I mean, I can make, at this point, I could make another compute shader that just writes to the, instead of doing a blit. Yeah, our plan for visualization didn't really work out because we don't even know if the values are correct, and if the values are correct, basically we know nothing right now. Okay, let me add the barrier, commit the code, and then we can try to, since we don't have a debugger, we can try to actually show the pyramid on screen. And then we probably won't really have time to go. Oh, this is incorrect, by the way. And then we won't really have time to go into culling today, but that's fine. Can do it tomorrow. Seems correct to me otherwise. Write only, read only. This isn't truly correct, I suppose. Because like the image is depth, technically. But maybe this doesn't matter. And I want to switch to samplers here anyhow. Let's do this. Oh yeah, we already know this works. Never mind. Okay, yeah, let me add a barrier and then commit the code, and then we'll see. This is not the most efficient barrier. There's a way to make it slightly tighter, but I don't think this actually matters in the current GPUs that much. Or maybe it does. It might. I don't know that it does. So for now, and there is a way to make this reduction much more efficient anyhow. So for now I will not bother. Just add a barrier. This will change nothing, but it's fine. And I just want to commit the code because we wrote so much code that we should really commit it. Making progress towards depth pyramid. I'll need to add a shader. So build depth pyramid, like split render pass into two, and sort of brute force way to visualize depth pyramid data. which doesn't really work, but you know. Yeah, okay. All right. So I kind of want to see something on screen. Like, it's pretty clear we won't really have time today to do culling, but this is fine. I kind of want to see something on screen that resembles a depth pyramid, right? And right now we see the black screen, so that is not good. I am worried that I guess I might need another compute shader or something that actually like writes to this swap chain from compute. Yeah. So that I can like do the depth conversion. Well, I guess I tried to do depth conversion. I guess right now it feels like our code just doesn't work. Like, it doesn't fill the buffer with, well, no, it did fill the buffer with something useful, never mind. What doesn't work? Maybe the read from depth doesn't really work for some reason. I'm not sure why that would be, but this is possible, right? Yeah. So yeah, not sure what happens right now. Like, our code doesn't really work, it appears, because it's almost as if the reads from the depth, unless I'm just like not thinking straight about the depth values that are there. But the thing is, so we are using an inverse depth buffer, so we are storing values, roughly speaking, that are z near, which is like 0.01, I suppose, so it's pretty small, divided by depth, divided by, let's just call it depth, whatever, like by the distance in world space units from the camera plane, which should be, our far plane was like around 100 units, whatever the unit is. So when this value is 1, then we are at z near, and then the smaller its value is, the larger the depth value is, so the further we go out, you know. And then z near, I think it's 0, 0, 1, but let's see. Yeah, z near is 0, 0, 1. So really, this is our distance, right? So you would think that if you do something like 1, so this is, let's just call z the distance from the camera to the pixel in world space units, and then depth, the actual depth value that's stored in the buffer. So you would think that, you know, z is, if you divide 1 over depth, then you get like z times 1 over 0, 0, 1, so it's like 100z. So you would think that if you do this, right, then you get back to z, and then you can divide z by some value to give you the world space depth, right? That is between, say, 0 and 1. But it doesn't seem to work. Let's try this again. Like, if this value is correct, which it might not be, then it seems like it should have worked. So but maybe this is not even right, and because of this things break, because I don't think this is right. So 0, 0, 1 over depth x, that shouldn't really be just z, and then we divide by 100, and then we should get something sensible. But it looks like we just get 1 somehow, or something really close to 1. It's fine, it makes sense that it's red because it's just one channel, but it looks like we get a value that's really large, which would mean that depth.x is really small. So it's as if depth.x is just like 0. Let's see. So yeah, so all of these values, they read out as zeros. And I don't really understand why that is the case. Did we like mess this up somehow here? No, for the early pass we are using store on the depth attachment. And then it's still this guy, but then we convert it, I thought. Let's check this. Yeah, to read only optimal. I feel like the problem is in the format, because it just doesn't make sense that anything else would affect this. Can I do D32F here? Not really. Can I do this without a format? Not supported for this version, so this needs some extension. So you know what, I kind of want a sampler here anyway, so let's just do that. And then I will want a size. Like and width, height, basically. And then instead of image load, I need just texture, I think. And then we'll just say that we will take the position, we'll cast it to vec2, and then we'll divide it by, and this should be float, I guess. This, I guess, should be just vec2 size, right? And then this could be image size. Does that work? So let's try doing that. We'll need a sampler, but we kind of want a sampler anyhow. So maybe that somehow works out in our favor. Because yeah, I think the problem might have been that the source image isn't really a floating point, like its depth, it's not really R32F. But I don't know, it's hard to tell. Or maybe the problem is deeper somehow. I don't know what the problem is then, if the problem is deeper. So let's try that. We'll need two things. We need to pass this data to the shader, and we also need to change this to a sampler, to a sampled image rather, which is like sampler and image combined. Depth reduce, depth reduce. So do that. Oh, we aren't including vec2. We can, no, wait. Start doing that. Okay. Okay, and now we need a sampler. So we need to use this constructor that can give us sampler. So let's call it depth sampler. I don't know. And this is an object that we need to create. So let's do that. Let's just straight out add this here, because yeah. VK sampler. I guess it could be like here, it doesn't matter. For now it will be nondescript with no arguments, and then we'll figure out later what we need to be customizing. Oh yeah, there's like a lot of things here. So, don't care about that. I think you have to set basically min LD and max LD yourself. Is there like... Yeah, no. Let's just set it to like 16 or something. Doesn't really matter. So we are not using comparison, so that's fine. Not using anisotropy, not using MIP bias stuff, but we will need to fill everything else, and except for this, we will need to fill these things essentially. Whoa. Oops. So yeah, so for now let's just do nearest MIP map nearest and then clamp on all axes. Okay. And later we might want to pass some of these parameters to the creation function, but that will be later. No, not sampler, depth sampler. Oh, and I need to pass this obviously to something. Oh yeah, okay, I'm already doing that. Okay. I don't know, let's see if that works somehow, especially if... Okay, our support for sampler objects I guess wasn't quite right. Let us see. Type mismatched, expected combined... Oh. Interesting. Right. I meant to use combined image sampler. I don't know, there's some weirdness in GLSL with respect to separate sampler objects. I forget if this is fixed by now or not. For now, yeah, let's say that it wasn't. For now, let's say this is what I wanted to do. Okay. So let's do the same thing here where we say if depth was 0, then we will write like half, otherwise we'll write 0. Okay. That is way better. So I'm guessing that the validation layers didn't catch the fact that I was reading like a depth texture as a non-depth texture and whatever. So what you see, I guess, is that now our shader does work. It's just that the values are so close to 0 that if I just output raw depth, then it's hard to see because, you know. Let me do this and hope. Well, hope is not a plan. Oh, if I increase the near plane, then I think I might start seeing things. Let's increase it to 1. Okay, finally. All right, great. Basically, with the near plane, that's 0.01. All values that you see, they are so close to 0 that when you convert them to a value that's between 0 and 1, they just are like 0 and you see black. But now we can clearly see that something finally started to work. Now, hopefully, let us do this. Yeah. Instead of P, we'll say that if I guess it's kind of weird. No, that's okay. So if the key is how they're ordered, yeah. If we are pressing like a number between, I could still, I don't know why. I guess I could still do this, right? Yeah. And it's just that, and that, and that. Okay. Okay. All right. Great. So the thing is, my sampling right now is not conservative because it's picking like one value, right? And it seems like it sort of works, but it's a bit more like it could be that for some of these pixels, there are actually pixels that are closer to the camera than the, farther from the camera than the value in the pyramid level designates, because we aren't doing the minimum, we aren't taking the minimum value, we're just taking a value. But that's easy for us to fix. I will do this in a second. Otherwise, things seem to work. I also need to offset, I guess, the sampling by like 0.5 or something, because otherwise things get weird. Yeah, we're not really doing the reduction carefully right now. That's fine. So let's fix that and then submit this, because finally, okay, so now basically depth pyramid works, right? We aren't using that yet for culling, but depth pyramid works. Actually, yeah, so here you can kind of see, like, I would expect, so wherever the mouse is, so this is the ear, right? Like, I would expect the values in this region to be roughly the same for a conservative test. Probably. Oh no, this is the farthest value actually. Yeah, I would not, sorry, I keep mixing that up. It should be the farthest value. So actually, I mean, we aren't making an effort to make sure things are conservative, but they might not be that terrible right now. Like, this pixel is kind of wrong, but this is because our sampling right now is kind of wrong. Oh, and we are dividing by the wrong thing, aren't we? well, we are dividing by the right thing, but we are not adding enough. Anyway, yeah. So there's a couple of bugs in our sampling, and we aren't using four values. So let's fix that. I'm glad things work finally, because it's painful to debug without a debugger. So yeah, this should be like we should be adding half of a pixel for complex reasons. I forget which. Yeah, so this looks more correct, sorta. And then we really should be doing texture gather. That it's the same, basically, yeah, same thing. Texture gather will return us 4 values around the point that we are sampling, which I want to say in this case will be, yeah, the 4 value. Yeah, so then we will need depth, let's call it depth 4, and then flow depth will be min depth for x, depth for y, depth for z, depth for double, depth for w, and then we can do that. And then we will still need to cast it to vector, but why not? Alright, so actually this is more what I would have expected, I think. Yeah. So this, I think, is now correct and conservative from the looks of it. Here's what happens. It's hard to see. In a really nice world, I would overlay one image on top of the other, but we are doing this hacky image blitz, so it's hard for me to do. But here's what happens. So you see these 2 pixels, all the really large pixels, right, of the depth pyramid level. So this is the value. They accumulate the value of depth in them with the min function, as in this is the farthest pixel. Did I use min or max? I think it's min, right? Yeah, okay, good. Farthest from the camera, right? Let's look at this pixel. This pixel says, well, oh, and the values are weirdly inverted because, are they? Well, no, they aren't. It's just really like values that are close to red are close to 1. So these mean things are close to the camera, right? So for this value, this is saying, hey, there are some pixels, some small pixels that contribute to this pixel in depth pyramid that are kind of far away. And if you see, this is true because this corner, the corner of this pixel is kind of here. And there is a lot of objects far away, right, that are much further than this kitten. So I think this is correct. This seems correct and conservative to me. This is what I would expect. And then this means that if there is a small object, we'll call this using some smaller, like small level of this pyramid, like this one. So if there is a small object, then and it's kind of here, then we'll call it using this data, which means it has a high chance of being occlusion called. If there's a very large object, like really large object, then we might call it against this kind of data. And then in some cases, the large object can say, I think I'm visible, even though maybe it's not, but hopefully this doesn't happen too often. Okay, phew. So, kind of tempted to stop here. I feel like if you spend half an hour more, we will actually get occlusion culling working, but we still have tomorrow. Oh, there's still a complicated thing, which is that we need to convert a sphere to a bounding box. And we still have tomorrow to figure this stuff out. And I think it might be better if we just stop now and just do a reasonable stream tomorrow where we continue this. Where we are is that we have done all of the preparation work except for the actual culling. Most of the preparation work for culling, we need to do this thing where we remember the data from the previous frame. So we need like an extra buffer, but that's super easy to set up. And we'll need like an extra shader to do occlusion culling, but we have done most of the work necessary. We have a depth pyramid. We even have visualization for it. and then we can just use this data to do culling tomorrow. Oh, and the final thing I want to do today before we finish, I want to leave it to do here that there's an extension, sampler min something, sampler filter min. So there is this extension that could be used so that we don't have to do a gather. Could be used instead to avoid the need to do 3 mins manually. I don't know if this is really faster, but it might be. Maybe at some point we'll try that. Not truly necessary. The other thing I want to do is I just want to add a timer around depth pyramid building. I'm expecting it to be not super fast because this is not a very efficient way to build a pyramid on modern GPUs, but I just want to make a timer here because that way we will know how long that takes. Yeah. And this guy. I could include the bearer in that. I suppose it would be honest. Sorta. It's not that honest. Whatever. So 4 and 5 will be the markers that we will use. And this will be pyramid GPU time. 5, 4, wait. Hold on. Oh. Oops. Yeah. Okay. It takes like 0.03 milliseconds to build a depth pyramid. So maybe we won't really optimize this because it will be really hard to optimize this and actually track the number. Like, you can build it faster. You should be able to, because there are some inefficiencies right now in this code. But if it takes 0.03 milliseconds, then maybe I just don't care. And this is like without vsync, so it's not super stable timings, but whatever. Let me double check that yeah, like before and after. And bottom of pipe. Should wait for computing now. Okay, maybe I don't care about performance then. Because that's in this, like, it's fast enough, right? 0.03 is not something I would want to optimize for this GPU. And also it's not something that we can easily optimize for this GPU because the timers are so, like, the timing is so small it will be hard to see the deltas and it will be a bit painful. Anyway, okay, I will not care about this then, so that's good. So yeah, that's kind of all I had for today. We will complete this tomorrow and actually implement culling using the data that we have generated today. Hopefully should not be too hard, and then I have a couple of smaller things that I want to finish with tomorrow, and then maybe talk about possible future things that may happen, who knows when. Fract log to depth. Yeah, so you could like output a depth logarithm. Again, I'm dealing with the weird problem of I'm too lazy to write another compute shader, and I'm doing this with the blit. Blit can't do a logarithm, right? Yeah, like, it's nicer to visualize logarithm of depth. We can do this. The problem is that this will break our like reduction step. So you could do this, right? I don't know if I want a logarithm of depth I think I might want to do... Well, you kind of want, like... kind of want this or something. No, but then you have to scale it. Yeah. You know what? Let's just not go there. Oh, no. Okay. Yeah, actually, that might be fine. Nah, okay, whatever. I don't want to think about this right now. Like, you might... There are nicer curves that help you visualize depth, but we don't really need them anymore, because turns out if you switch the near plane to 1, then values start from 1 at the near plane, and then they quickly go to 0, but you still see... like, basically at... the minimum value that you could display on the screen is like... come on, is like this, right? 1 over 255. 1 over 255. But turns out that with the near plane 1, we are writing values that are 1 over z, where z is the distance from the camera. So it turns out that 1 over 255 represents 255 in world units, which I think our bounds are close to that. Of course, it's going to be very hard to see 1 over 255 on screen, but draw distance. Yeah, right. So we kind of, with a larger near plane, our depth distribution is good enough so that we don't have to do other conversions. Of course, we might want to trim the near plane back later, but right now we don't even see visible clipping on this scene, so even near plane of 1 is fine. Yeah. Okay. All right. If there's nothing else, then thank you, everyone. And again, tomorrow we will actually use this data to do actual culling, which will be fun, hopefully. And hopefully we will not have to parse any more SPRV that we did today. Oh, and I should commit this and push this before we end. So yeah, I guess the biggest issue was, the bug was like we didn't have a sampler and things didn't quite work. And this is a bit of a hack. I'm currently assuming that we aren't using sampled image without combined, but it seems fine. Day 13, depth pyramid works. We've used the sampler instead of an image load to make it work. Together. The reduction is slightly non-conservative, I believe, for some odd values of the swap chain sizes, maybe, but we will not deal with this. Like, I think if I do the math really carefully, it will end up that the first reduction that we have can be slightly, or even subsequent reductions in theory, can be slightly non-conservative, because so like if you reduce 3 texels to the next MIP level, you get 1, because 3 over 2 is 1 in integer coordinates, right? Which means that you have to be reading 3 texels from the original image to do the conservative reduction, but we are only ever reading 2 by 2. So we are never reading like 3 by 3, right? So if you are doing like 3 by 3 to 1 by 1, right now we are reading something. We are taking like the center, and then there's some, based on the routing errors, we'll read like 4 instead of 9 texels out of the source image. So it's like mostly conservative. We still are somewhat non-conservative for non-power of 2 swap chain sizes. For example, 3 by 3 to 1 by 1 reduction needs to read 9 texels instead of 4. But, you know, it's fine. Like, we might come back to this and fix this, or we might just say good enough. and then push. And then the stream is done. Alright, thank you, see you guys tomorrow. Wait, did it push? It pushed.